Okay, so thank you for the invitation. This has been a lot of fun for me so far. And I'm going to tell you today about proof by pictures. And okay, here's a really common story in mathematics. Somebody is working away late into the night in their attic room on something, and they start thinking about it a little differently, right? Not just the ideas actually start to make sense, but they stumble upon some sort of analogy that actually kind of works, that helps them explain things they couldn't explain before and gives them this intuition that maybe other people don't have. And this is a very common story in math, and usually it ends with the person using this analogy to prove some things in the more standard way, and then they present you, the mathematical public, with these standardized proofs. And so what's interesting about this story is that von Jones had this experience studying subfactors of von Neumann algebras. And instead of just giving us the results and hiding this analogy away, he decided that the analogy was as interesting as the results he was getting. And so he told us about it. And as is the case with analogies, it took 10 years probably for people to believe him that it worked, be convinced that it was a good way to think about things, and actually try to incorporate it into their own thinking. And the stuff that I'm telling you today is mostly from this framework he developed called planar algebras. Okay, but this is not the only proof by pictures framework. And actually a fair number of other people stumbled upon similar formulations for similar ideas. Some of them even also told us about them. So in the literature, you'll find spiders for Lie algebras by Greg Kuperberg, or you'll find diagrams for monoidal tensor categories. You'll see this framework in kind of lots of places in algebras. But since this is the one that I know and understand, this is the one framework that I'm going to use to tell you about this. Okay, and my presentation today is very much not historical. It goes from sort of the most obvious to the less obvious. So I start with things that obviously have this pictorial structure because they are pictures. And I kind of gradually will lead you away from that to things where the structure is a little less obvious. Okay, so the Temperley-Lieb algebra, the ingredients in this are Temperley-Lieb diagrams. And these are ways to draw pictures where you have endpoints on the top and endpoints on the bottom, and you connect points with strings, right? Every string starts at one point and ends at another point, and the strings are not supposed to cross each other. So here are some examples of Temperley-Lieb 4, 5, or 7 diagrams. And we think of these combinatorially. So we can say that topologically, these are the same means that they're actually the same. And OK, little asterisk here, that the strings are meant to go from the bottom line to the top line, or from the top to the bottom, without kind of going outside of this interval. OK, so no winding around the outside and connecting up from the bottom. OK, well, if we have endpoints on the top and endpoints on the bottom, how many Temperley-Lieb diagrams do we get? Let's see. If we have 1 point on the top and 1 point on the bottom, there's exactly one of these. If there are 2 points on the bottom and 2 points on the top, then you can either go straight up and down, or you can have a little cap and a little cup. So there are 2 of those. And when n equals 3, you should check that I've drawn all the different possibilities here. There are 5 of these. Does anybody recognize this pattern? Yes, it's the Catalan numbers. So if you, at some point later on in this talk, are lost or bored, you should try to find a bijection between these Temperley-Lieb diagrams and something that you know the Catalan numbers counts. The Catalan numbers are there's 150 different things that they count in Richard Stanley's book. But I think most people see them presented as the number of ways to write down 2n parentheses that are allowed by the rules of parentheses. So to close a parentheses, you have to have first opened it. Anyways, figure out what those have to do with these TL diagrams. Here's another thing we can do with Temperley-Lieb diagrams. We can multiply them. And here multiplication means take one and stack it on top of another. Okay, and what we get is still data about connecting points on the bottom to points on the top. As you can see from this first picture here, right? We keep that cap on the bottom, and the third point on the bottom gets connected through a little bit of a windy route to the first point on the top. OK. But what happens in the second case? We've created a loop of string. What do we do with that? That's not part of our Temperley-Lieb data. We can't just leave it there. So the short answer is that we throw it away. But we remember it was there. We record this factor delta. Every loop we throw away, we multiply the result by delta. For now, think of delta as just some arbitrary complex number that I haven't told you the value of yet. OK. Well, if I'm calling this multiplication, there's some properties you expect it to have. Is it associative? Sure. So we have 3 blocks here. And if I put the middle on the bottom and then the top one on that, that's the same result as if I go down the row and put the top on the middle and then both of those on the first. So this is associative. Good. And this is, now that we have this multiplication, we start thinking of Temperley-Lieb as an algebra. OK, so our basis is these Temperley-Lieb diagrams. We're looking at their span over the complex numbers. Addition is formal, right? We're just treating these as a basis. And multiplication is this multiplication by stacking I told you about. Just take the linear extension of that. If you have to multiply a plus b times c plus d, just FOIL that out. And now you have 4 resulting diagrams. OK. Yes?
On the previous slide, the picture, if the line went to the left of the loop, would that still end up with the same product in the end?
Yes, good question. It doesn't matter where these loops are. They can be anywhere in the picture. They can be nested inside each other or sitting next to each other, anything like that. So this is almost as good as just forgetting they were there, right? We lose information and we just don't care.
Another question.
Yes?
So each time you throw a loop, you multiply by the same delta? Or?
Yes. Yes, it's the same delta every time you throw away a loop. Any more questions? OK, awesome. So now, we already counted Temperley-Lieb diagrams, but I started at TL1. What is TL0? How many ways are there to connect 0 points to 0 points? Yes, there's exactly 1. Right? So this is like the empty diagram. But we take the empty diagram as our single basis element, and so we get a one-dimensional vector space. Now, this is useful because this diagram here that I've drawn, where you take a Temperley-Lieb diagram and you connect all the strings on the top to all the strings on the bottom, is now a map from any Temperley-Lieb space into TL0. And it is a trace, I claim. OK, so what does that mean? Well, it means that we're producing a complex number. And one of the properties you expect traces to have is that they're cyclically commutative, right? The trace of a times b is the same as the trace of b times a. So let's imagine we took 2 of these diagrams and we multiplied them one on top of each other. And now we connected all their strings up. Why is this the same as if we had multiplied them in the other order and connected their strings up? Yes, because we have this, we can take this one on the bottom and drag it along the side and back up on the top. OK. And this is only the tip of the iceberg in terms of additional structure on Temperley-Lieb that you get using diagrams. Yes? Right, so delta, I said, think of it as an undetermined complex number. Right, so don't think of it as a variable. Right, that's a strange distinction to make, right? But like, it's going to be a complex number. Think of it as some complex number whose value you haven't been told yet. Thank you. Yes?
So how do you get the output complex number? What's the value?
Oh, good question, right? So say we had this, and we took its trace. How many loops do I have here? 2. And so this is delta squared, which I'm insisting of thinking of as a complex number instead of a polynomial in delta. OK, we get all sorts of other structure on Temperley-Lieb coming from pictures. And I'm going to show you this next slide, and it might not make a lot of sense. But OK, we have, in addition to the multiplication I already told you about, we can multiply in different ways. We can choose a different subsets of the strands to connect up to each other. So this here is a co-multiplication. I set A and B down next to each other and connect the left strands to the right strands instead of the top to the bottom. Again, you can see that it's commutative. It's like, sure, fine, you can call that a multiplication. On the one hand, it's not so clear why you would do that. And on the other hand, it's not so clear that it's inherently worse than the multiplication we've already defined. These two are pretty good. You can include the various Temperley-Liebs in the next one up by adding on a strand on the right. And the inverse procedure is a conditional expectation that takes you from TL2n plus 2 down to TL2n by capping off a strand on the right. Yes?
Can you say more on how the co-multiplication is commutative?
I should not have said it's commutative. It is associative. That is the word I was looking for. Thank you. Yeah, it's very much not commutative. OK, and so this conditional expectation and this inclusion are inverse to each other up to a factor of delta, right? If you were to include and then expect down, you'd end up with delta times your original element. And so this gives not just this turns Temperley-Lieb into a whole family, a bunch of things that interact with each other instead of just a different one of them for every value of n. OK, and I'm going to come back to this word later on. But for the moment, I'll just say that this basically gives Temperley-Lieb the structure of something called a planar algebra. OK, now I know that some of you are not theorists. And so if that is the case, you might want to start thinking about this parenthesization problem, because I'm going to say some kind of obvious stuff for a few minutes here. We'll begin with a definition. A knot is the image of a smooth embedding from the circle into Euclidean 3 space. For example, OK, so which is more important in a function? Is it the domain or is it the range? Are knots more like a one-dimensional thing or are they more like a three-dimensional thing? I'm glad that nobody answered because it was actually a trick question. The answer is no, that knots are two-dimensional. I mean, they're not actually two-dimensional, but almost all of the structure of knots you can see in 2 dimensions, right? They have these tiny regions where they are not two-dimensional, but they're always, in a presentation like this, not two-dimensional in a very particular way that's, in fact, identical from place to place. So they're really like two-dimensional things with just a little tiny bit of extra information. Right, and so if you study drawings of knots on paper or blackboards or wherever, then you quickly come upon the Meister moves, right? So when do 2 of these doodles of knots in the plane represent the same knot? Well, that's true if you can get from one of them to the other one doing the moves shown here. So Meister 1 takes a single strand and pulls a little twist out of it, pulls it straight. Meister 2 takes 2 strands that cross each other and pulls one over the other, so then they're just running parallel. And Meister 3 has 3 strands, takes one that crosses 2 other ones, and it just sends it across a crossing. So this is yes?
Is there a distinction between crossing over and crossing under? Is there like a reference to one, reference to
Yes. Yeah, I mean, there are, right, so I've written these down here, and in fact, if this crossing was the other one, we could still do Meister 1. If the right-hand strand and the second one was on top instead of left-hand strand, we could still do it. So I'm being a little sloppy about that. But so these Meister moves are fantastic, and it's easy to remember which is 1, 2, and 3, because the first one involves 1 strand and 1 crossing. The second one has 2 strands and 2 crossings, and the third one has 3 strands and 3 crossings. OK, so how do you use these to see that 2 knots are the same? It turns out it's a giant pain. So if you're used to taking 2-dimensional pictures like this, and kind of if your brain can turn them into 3-dimensional information, you can sort of pick through, like, how am I going to get from one of these to the other? So what I'm about to do here is take this arc of rope and move it across this crossing. And I'm actually going to do 4 Reidemeister moves in the process, but I'll just draw it like that, and your brain, that is a reasonable thing to do. So these Reidemeister moves are slow and painstaking, but on the other hand, they generate all isomorphisms between knots. So, okay. And so we can do these Reidemeister moves patiently, and then maybe not so patiently, to get from one knot to another one. Okay, but suppose that I was mean, and I gave you a homework problem, which was show that 2 knots are the same, or decide if 2 knots are the same. And you spent an hour working on this. And at the end, you couldn't turn one into the other, no matter which Reidemeister moves you do. That doesn't prove that they're different, right? I mean, and if you don't believe me, if you think that you could figure out questions of knot isomorphism in an hour, think about those puzzles that have like the horseshoe and the string and the ring and the rope, and you have to like take the thing off the other thing, right? And these things always seem impossible, and then like your uncle or your aunt or whoever's it was is like, oh no, look, there's a trick. And anyways, these applied topology problems are surprisingly hard. So if we think that 2 knots are different, and we can't Reidemeister one into the other one, how do we prove that they're different? And so this is why we have knot invariants. Okay, and a knot invariant is a pretty simple idea. It's you take a knot and you somehow associate it to something that is simpler than a knot. So for instance, a complex number, or maybe a polynomial, or there are even knot invariants that take knots and send them just to kind of simpler diagrams. And if you construct your invariant so that doing the Reidemeister moves doesn't change its value, then what you have is a way of telling knots apart. If the invariant gives you 2 different answers, then you know that knots are different. Okay, and of course, if the invariant gives you the same value, you may not know that your knots are different. There can be knots that are different but that have the same value of any of these invariants, because of course knots are more complicated than these other things we're mapping them to. Okay, and so here is a particular knot invariant. This is the Kaufman bracket, which will give rise to the famous Jones polynomial. Okay, so for now, we're actually going to think of delta as a variable, not just an unspecified complex number. And we choose a number a, or we choose a variable a that satisfies this relation. Okay, and now we define what we call a resolution of a crossing. So anytime you see a crossing like this, you replace it with 2 different uncrossings, right? The 2 different resolutions of this crossing are for the strands to go straight up and down or side to side. And so we have a single knot, and we apply this relation once, and now we have 2 knots. They each have 1 fewer crossing, and they differ in this particular location, right? So what this says to do is to kind of fix the rest of the diagram of the knot and only change it in this local way. All right, and then the second relation is that when we see a closed loop. So imagine that there's some other part of this diagram, but there's this closed loop that's not linked up with any other part. When we see that, we throw it away and we multiply by delta. Okay, these 2 relations are enough to let us define the Kaufman bracket. We can now associate a polynomial to any knot presentation. So let's do it. So first, we're going to resolve this crossing. And if you are a very careful person, you'll notice that that crossing seems to be not the same as the crossing on the previous slide, right? So this one, the overstrand has a slope of -1, and here my overstrand has a slope of 1. But these are meant to apply in sort of any planar way. And so notice that if you just turn your head 90 degrees, you get the other kind of crossing, right? So just imagine rotating each of these 90 degrees, and the relation still holds. And so that's what we've done. With the coefficient of a, we have straight up and down. And over here, we have left and right with the coefficient of a minus. And now we have one fewer crossing, and we can apply this relation again. In this case, in the place that I've highlighted in red, we're going to apply it, and we get 4 diagrams. And now we do it one more time, and we end up with 8 diagrams picking up these coefficients. And now we start using the relation that lets us throw out these unlinked loops. Right? So every time we have an unlinked loop, we get a factor of delta. Delta cubed for the first one, delta squared for this, and then just delta here, and here, and here, and delta squared again here. So you plug in these deltas, you chase through some math, and you get this polynomial. OK. I've told you this whole process, but I haven't told you that it's an invariant, right? I've told you how to compute it. How do we see that this is a not invariant? Well, for one thing, we could take our Meister 2 diagram and just apply the resolution relation for these two crossings. And so if we do this, we get the following. And this here explains why a and delta, why a was chosen to be minus a squared minus a to the negative 2. Right? That's the one choice of a that will make Meister 2 work out and give us a coefficient of 0 right here, so that this really is equal to that. OK, here's the good news. Meister 3 also works. Here's the bad news. Meister 1 doesn't. OK, so this is actually fixable. I'm not going to talk about how you do it, but basically you bring in another not invariant that also goes wrong with Meister 1, and you make the things that go wrong cancel each other out. It's pretty cool. OK, and if you do that, you get the Jones polynomial. And as you maybe have already heard at this conference, the Jones polynomial is pretty good at telling knots apart, but it's not perfect. So we heard yesterday about an infinite family of knots that all had the same Jones polynomial. And so it's known that the Jones polynomial is not a complete invariant. On the other hand, it's an open question whether there exist any knot which has the same Jones polynomial as the unknot, as just a single untwisted loop of string. And here's something even more interesting. It's known that there are links, non-trivial links, that have the same Jones polynomial as trivial links. So it's really like, we know that the Jones polynomial isn't very good. I mean, not that it isn't very good, that it's not perfect at telling knots apart. It's not perfect at telling links apart, but it could be that the Jones polynomial is good at telling you, is something knotted, yes or no? We don't know. OK, and now we're ready to define a planar algebra. So we're going to start with something called a planar diagram. A planar diagram has some number of circles on the inside, and you should think of these as like holes punched in this disk. Okay, these are boundary pieces, and then the outside circle. Within the part of the disk that hasn't been punched out, we put strings that don't intersect, and they have their endpoints on the boundary, either the inside boundary disks or the outside boundary. And now, for each boundary circle, I'm going to choose a marked point that tells us just kind of where to start here. OK, and now we can put all of these together, these planar diagrams together, to form an operad. I'm not going to tell you what that means if you don't know, but let's just say for now that you could compose two of these diagrams. If the number of outside strings matched up with the number of inside strings, you can imagine picking one of these up and shrinking it down and putting it down inside the other one. And that's why there are these little stars. They tell you how to line things up if you're going to do that. OK, so with this structure, we have an operad. But I don't really need that to tell you what a planar algebra is. So a planar algebra is a family of vector spaces that these planar diagrams act on. OK, and there should be one vector space for each non-negative integer. And then these planar diagrams are supposed to give us multilinear maps among these spaces. So y, v2, v5, and v4, y, v7 here, because this disk has 2 strings. This disk has 5 strings. this one has 4, and the outside disk has 7. Okay? So what you should imagine is that you're picking up this V2 and putting it down like as an input in here. V5 gives you an input that goes in here, and V4 gives you an input that goes in here. And then there's some mechanism for creating an element of V7 as an output from those inputs. Okay, and there are some axioms that I'm not going to get into. These axioms say things like composition of diagrams should be the same as composition of multilinear maps. Anyways, so we've already seen some examples of these. Temperley-Lieb is a planar algebra, okay? And it's nothing fancy is going on with Temperley-Lieb, right? Planar diagrams act literally by insertion, right? If you have, you know, a Temperley-Lieb diagram that has 4 points on the bottom and 4 points on the top, then that gives you an element of TL8. And anytime you have a disk with 8 inputs, with 8 strings coming out of it, you can plunk this Temperley-Lieb element down inside there and make the star line up with the left side of the diagram, say. Okay, and then of course, if in this process you create a loop of strings somehow, then you throw it away, but you multiply the result by delta, just like we've been doing all along. Okay. Nothing actually super complicated there, bless you. Now, here's another example of a planar algebra, the planar algebra of tangles. Okay, so a tangle is just like a knot where you don't demand that all the ends match up. So it's some bunch of strings that have been knotted together, but you have some number of strings that you've arranged around the outside. Okay, so we can take these tangles as a basis for a vector space and consider them, of course, up to isotopy. And we get a planar algebra. Again, planar diagrams act by just inserting the tangle you have into the picture and taking that result. So we're seeing these examples where our input is actually pictures and our output is pictures, right? And so that's, like I said at the beginning, we're going to start with the ones that are more obvious and move on to the ones that are less obvious. Okay, one advantage of thinking about this is that the Kaufman bracket is then a homomorphism of planar algebras between tangles and Temperley-Lieb. Yes? Yes. Well, tangles are planar diagrams considered up to the Meister moves. Yeah. Other questions? OK. Cool. So now let's do a slightly different example of planar algebras. So you guys have heard of the 4-color theorem, I'm sure. There are all these theorems about how many colors do you need to color in a map so that whenever 2 countries touch, they have like they share a border, they have different colors. People who make maps are totally uninterested in this question, right? They will use 7 colors, 8 colors, 9 colors. They don't care. Mathematicians care. OK, so a graph can be n-colored if you can color its faces using n different colors. And right, if we're talking about graphs and coloring them and their faces, we're imagining that they're embedded in a surface. Okay, so you can talk about n-coloring graphs on the torus or the 2-hole torus or whatever, but for me, for this talk, we're going to stick with planar graphs. Okay. So the degree of a vertex is the number of edges it has coming into it. And we're going to see some theorems that relate that degree to the colorability of the graph. So the first theorem is the 2-color theorem. Any planar graph where every vertex has even degree can be 2-colored. Okay, and this isn't hard to do. Start with some region and choose not to color that region. And now for any other region, figure out whether it should be colored or not by taking any path from here to the original region and counting its parity. And the distance from the region is not invariant, but the parity of that distance is, because every vertex here has even degree. OK? OK, that wasn't hard. 3-color theorem So there are actually kind of a variety of different three-color theorems. There are a number of setups where you can guarantee that you can color your graph using only three colors. The easiest one to state is that a planar graph with no degree 3 vertices can be three-colored. OK, and now the 5-color theorem says, without hypotheses, that any planar graph can be 5-colored. The interesting thing here is that Kemp in 1879 thought he had proved the 4-color theorem. And it was a decade until Heywood came along and read what he'd written and said, hold on, this is crazy. You have only proved the 5-color theorem. OK, and it would be almost a century until the 4-color theorem was actually proved by Ken Appel and Wolfgang Haken in 1976, that any planar graph can be 4-colored. And this is famous because it was the first big proof in math to use computers in a substantial way. OK, so the main ingredient, maybe not the main ingredient, but the first ingredient, if you ever want to prove something about a planar graph, is always going to be the Euler characteristic. The Euler characteristic of a planar graph is the number of vertices minus the number of edges plus the number of faces. And if your graph is planar, this quantity is always 2. So here's an example where we calculate it. You can check for yourself. This is not hard to prove. It is surprisingly useful. You can get a lot of mileage out of it. Appel and Haken used something called discharging as the theoretical framework for proving the 4-color theorem. And it's basically based on using this Euler characteristic, taking that 2 and dividing it up among the faces of the graph. Yes?
If you have a non-planar graph, how can you talk about the number of faces it has?
Right. So it would have to be embedded on some sort of surface. Right? So if you have a graph embedded on a surface, whatever that surface is, you can compute the Euler characteristic. But you're absolutely right. If it's just kind of an abstract graph with vertices and edges and not any sort of embedding, it doesn't even make sense to talk about the number of faces. OK. So as a corollary of this definition theorem, every planar graph has a small face, a face which is either a bigon, a triangle, a quadrilateral, or a pentagon. And you can convince yourself of this pretty quickly, right? If you start trying to draw a graph consisting only of hexagons, you will very quickly OK, Asterix here. Every planar graph which does not have degree 2 vertices, right? What's a degree 2 vertex? It's a vertex that only has 2 things coming out of it. It's kind of just like a vertex in the middle of the edge. So if all your vertices are degree 3 or higher, you have to have a small face, right? And if you start trying to just draw something that has all hexagons, you'll see that it never wraps back in on itself. You can tile the plane with hexagons, but you can't make them do anything finite. And once you throw in 7 gons, 8 gons, 9 gons, it just gets worse. OK. So, I wish. This is a proof of the 5-color theorem. OK. And so the first thing to do is to turn this into a problem about graphs where every vertex has degree 3. So if I can color this thing, then I can definitely color this thing, because all I've done is deleted a face. But every pair of faces over here where the edges touch, they still touch over here. And so if we have a graph, and we replace every degree n vertex with a small n-gon face, then we haven't changed the colorability of the graph. But we've made all the vertices have degree 3. And so if a coloring theorem is true for graphs where every vertex has degree 3, it's true for all graphs. And so that simplifies things a little bit. OK, and so here's where the planar algebra comes into it. So this is called the color counting planar algebra. And the vector space Vk is functions from length k sequences of colors to numbers. OK? Now, I'm going to tell you how to interpret any planar graph as such a thing, as a function from sequences of colors to numbers. And that is to take your sequence of colors and count how many ways there are to color the boundary of that graph using that given sequence of colors and then fill in the rest of the graph in an allowed way. So that sounded pretty abstract. We'll do a couple examples and it'll make sense. So here's a graph. And if I'm told to color it in the order 1, 2, 3, then this region gets colored 1, and this gets colored 2, and this gets colored 3. And that's allowed. No adjacent faces have the same color, so we're good. So there's exactly one way to do that. And if I was given the sequence 1, 2, 2, then I would end up coloring this region and this region the same color, and that's not allowed. So there are 0 ways to color this graph with this sequence. And in general, if we have I, J, and K, then there's one way to do it if I, J, and K are all distinct, and there's 0 ways to do it otherwise. All right, how about a slightly more difficult example? Not really. Here's a triangle. And if I've given the sequence of colors 1, 2, and 3, then I color these outside regions. And now how many choices do I have for the inside region? I have n colors, but I'm not allowed to use colors 1, 2, or 3. So there's n minus 3 choices. Okay, or if the colors are 1, 2, and 2, there are 0 choices because we've already colored 2 adjacent regions the same color. And so now you'll notice that this is really just a multiple of this. So we can express that as just saying that this diagram of a triangle is n minus 3 times this diagram with a single trivalent vertex.
What is n again? What is n?
What is n? N is the number of colors I'm using. Yes?
I'm having trouble seeing how this is a vector space.
Good question, right? So let's go back. The vector space is actually sequences of colors, functions from sequences of colors to numbers. And what this is, it's a description of how to produce something in the vector space given, yeah, the functions form a vector space. And this is a description of how to take one of these diagrams and interpret it as such a function. Yeah, no, thank you for asking. Other questions? Over the complex numbers. I only ever think about the complex numbers. So I know that doesn't make me a very good algebraist, but. OK, so the same argument shows you that if you have a bigon like this, that this is n minus 2 times a straight line because of the number of ways to color this as part of a bigger diagram versus the number of ways to color this. And if you have a circle, then that's n minus 1 times the number of ways to color that same diagram with this closed circle removed. OK, we also have a less obvious relation that looks like this. And the way you can think about this is that this is the way to color a sequence of 4. If you have a sequence of 4 around your boundary, then if you look at all the different ways to color it, opposite sides can be either the same or different. And so here we have all the ways to color this with opposite sides being different. And here we have all the ways to color this with opposite sides being the same. And here we've taken our opposite sides to be the top and the bottom instead of the left and the right. OK, so this is less obvious, but if you sit down and work it out, it is true. And now this is so interesting because it gives us a relation that doesn't look positive, right? You can say that this I graph is equal to the h plus the straight up and down minus the cup cap. OK, and we can apply that along, say, one segment of the square to get this relation. OK, so this now lets us pop squares. And then we can apply it again along one edge of a pentagon, and it lets us pop pentagons. OK, and the exact details, especially of this last relation, are not at all important. What's important is the coefficients. OK? What values of n makes all of these relations positive? So If n is more than 1, we're positive. N is more than 2, more than 3. OK, n is more than 4. Aha, and here it looks like n has to be more than 5. OK, but actually, it would be OK if this was a 0, as long as this wasn't a 0. So as long as n is greater than 4, these are all positive relations. OK? And so here is an algorithm for 5-coloring a graph. According to the Euler characteristics, somewhere in it we have a bigon, triangle, quadrilateral, or pentagon. Find it, apply this relation, and now what we have is a smaller graph, where smaller either refers to the number of vertices or the number of faces. And so somewhere in here, there is a bigon, triangle, quadrilateral, or pentagon. OK, so just keep going through this, and eventually you'll end up with a bunch of coefficients times the empty diagram, and all those coefficients you know are positive. OK, so this doesn't just answer the question of whether a graph is 5-colorable or not. It actually answers the question of whether this graph, how many ways this graph is 5-colorable. OK, how am I doing on time? Does anybody know? 15 minutes? Perfect. OK, great. So the next thing I'm going to do is I'm going to tell you about subfactors. OK. Yes?
Can you please explain again why we care that the coefficients are positive? What does that tell us?
Yes, because we want to know how many ways there are to color this graph using 5 colors. And we don't want to actually go through this for every graph. We just want to sort of guarantee that any graph will produce a positive number as a result. And so because these coefficients are all positive, we know that however we sort of apply them in a row, however many new diagrams we end up creating, in the end we're adding up a product of positive numbers. And so we get a positive number as a result. OK, so I'm going to take a little bit of a sharp turn now, and I'm going to tell you just a tiny bit about subfactors. OK, a little bit of context. When we talk about subfactors, we're talking about von Neumann algebras. Von Neumann algebras are unital star subalgebras of bounded operators on a Hilbert space, which are closed in a certain topology. To be a factor, a von Neumann algebra should have trivial center. And then a subfactor is one factor that sits inside another factor. OK, and don't worry if you didn't understand that, because for the purposes of this talk, I'm interested in subfactor planar algebras. OK, and I don't mean to sort of discount the difficulties of subfactors. There are all sorts of interesting things going on in subfactors. And however, since this is an algebra conference, not an analysis conference, there's this tool of planar algebras that lets us get at subfactors without having to understand all that analysis. And so that's what we're going to be talking about today. OK, so a subfactor has this invariant that's called the standard invariant, because people who name these things are not creative. And what it is a planar algebra. So every subfactor has an associated invariant, which is a planar algebra. It's not just any planar algebra, though. It's a planar algebra with some bonus structure. And so that bonus structure is that we have an adjoint, which means that this bilinear form is actually an inner product. OK, so we can now do geometry on these subfactors. And I mean that in a very basic sense, right? I mean, like, we are really going to be proving things are positive by taking their inner product and showing that it's more than 0. I don't mean anything fancy there. OK, and if a planar algebra has these properties, oh yeah, the other significant property is that the first planar algebra in your space is one-dimensional. If your planar algebra has these properties, it's called a subfactor planar algebra. And subfactor planar algebras give rise to subfactors. Subfactors give us subfactor planar algebras. And so there are existence questions about subfactors that can be answered using planar algebras. OK, and these two conditions are really quite nice, that this P0 is one-dimensional and that the bilinear form defined this way is an inner product. So here is an example of a subfactor planar algebra. Temperley-Lieb. OK, if delta is greater than or equal to 2. Okay? TL0 is one-dimensional. We've already talked about that. That's fine. The positive definiteness is why we need delta to be 2 or greater. Okay? And that's a little bit subtle. Okay.
You said it's complex number with 2 greater.
Yeah, so in this case it needs to, so now I'm saying if it's a real number, which is greater than 2, then it's positive definite. Okay, so Temperley-Lieb isn't just sort of the first and most obvious subfactor planar algebra. It's actually completely foundational. And that's because any subfactor planar algebra contains either a copy of Temperley-Lieb or a quotient of Temperley-Lieb. Okay, so subfactor planar algebras have a value of delta just like Temperley-Lieb. They have a loop constant because the zero space is one-dimensional. And so a loop must be some constant multiple of the empty diagram. And historically, the value of this loop constant squared is called the index. Okay, and so if your subfactor planar algebra has that loop value 2 or more, it contains a copy of Temperley-Lieb. And if that loop value is less than 2, it contains a quotient of Temperley-Lieb. And so Temperley-Lieb is always there when you're working with these subfactor planar algebras. And in what I'm about to tell you, the sort of motivating idea is that there's not really a lot of structure in addition to Temperley-Lieb if you're looking at subfactors that are small in some sense. Okay? And so we can get a surprising amount of mileage from Temperley-Lieb. Okay, so I'm going to tell you a theorem. This is joint work with Stephen Bigelow, Scott Morrison, and Noah Snyder. And I'm not going to at all motivate the importance of this theorem. I mean, like, I'm not going to convince you why you should be interested in this other than it's a sort of strange-looking, interesting thing. So what we proved is the existence of the extended Haagerup planar algebra. This was a planar algebra, well, a subfactor, that was conjectured to exist in the 90s by Haagerup. He, in fact, conjectured this whole list of subfactors, and people sort of whittled away at them one at a time. You know, knock out one of the infinite families here, construct a couple here, and this was the last one on the list. And so it was sort of exciting that we were able to find it. Okay. And what I'm describing here is a generators and relations presentation of this planar algebra. So we have a single generator S that has 16 strands coming out of it. But this is a planar algebraic generator, which means that when I talk about things generated by it, I mean any diagram where you have any number of input disks with 16 strands, you can plug those all full of S's and connect them up in whatever planar way you want. So any diagram you can build out of any number of these S's is in this planar algebra. So we have one generator, and then we have some relations. And if you just look at them, these look pretty arbitrary. So let me tell you a little bit how to think about them. This first one here, the only difference between this and this is that I've moved the star by 2 clicks. And so this says that this generator S is an eigenvector of rotation. That if you do this rotation, you get back some multiple of itself. Here we have that this S is uncappable. Anywhere you take 2 strands that are next to each other and you tie them together, you get back 0. And what this means is that like S is not sort of S has no shadow in diagrams with 14 strings, right? There's sort of no, this is new at level 16, and it's not sort of growing out of some stuff that was there before. It's genuinely new here. Okay, this is a multiplication relation. We take S and we connect it to itself with 8 strands. And I'm not going to tell you what it is, but I'm going to tell you the result of this is in Temperley-Lieb. And so when you have 2 S's that connect to each other with 8 strands, you get to cancel that pair out. Pull them out and throw them away. Okay, and the remaining 2 relations are, so my collaborator Stephen Bigelow calls them substitute braiding relations. Meaning that in these planar diagrams, we don't have a braiding. We can't really pull strands over each other. But this particular generator has a relation that says 1 S under a strand is equal to 2 S's on the outside region connected to each other by 7 strands. And then this is also a substitute braiding relation. And this one says what happens when you pull S through 2 strands. And in that case, you get 3 S's connected up by 7 strands. OK. Now, sorry? Sure, some coefficient there. Yep. OK, now the theorem is that what we get from this is a subfactor planar algebra, and it's not trivial. OK, and that doesn't seem that easy to see, right? To see that it's a subfactor planar algebra, we need the 0 space to be one-dimensional. In other words, any network you can make by taking these S's and connecting them to each other, every S has 16 strands coming out of it, but there's nothing connecting to the outside. They're all connected up with each other. Anything you make with this is some multiple of the empty diagram. OK, so that's the big challenge. The other pieces of showing it's a subfactor planar algebra, so to show that it's non-trivial, we embed this planar algebra in a larger and easier planar algebra. And this part is actually sort of a pain, but it's a pain that's mostly done by computers, right? So there are like some 10,000 by 10,000 matrices floating around, but Mathematica takes care of them, so we don't really have to think about them. OK, but the fun part here, so the evaluation algorithm that gives us every diagram as a multiple of the empty diagram. We call it the jellyfish algorithm. And here's how it works. OK, so we have each of these S's is a jellyfish. And one morning the sun comes out and the ocean water is cold and they all want to swim to the top of the ocean to sit in the sunlight. OK, so each of them chooses a path from where it is to the top. And it doesn't have to be very clever, right? So S could have just kind of gone around the outside and gotten to the top, but whatever. We're just going to pick some path for it to get to the top. OK? And now that we have this, we start using our substitute braiding relations to let the jellyfish swim up. OK, and it's a long and arduous journey. And along the way, some of them reproduce, right? So these substitute braiding relations replace one S with 2 S's or with 3 S's. OK, so as our jellyfish swim to the top, there are more and more of them. This is a very heuristic diagram, right? Like, right, this is supposed to represent 9 strands right here. So we have to go through 10 strands, so that's 10 chances to double or triple. Anyways, the point is that we eventually end up with some diagram where all of our S's have made it to the top, are in this same outside region as each other. And so now we're going to sort of take a diagram that looks like this, and we're going to say, hey, this is just a funny way of drawing some sort of polygon, right, where all the vertices are around the outside. OK, and now I've done everything I need to do with the substitute braiding relations, and I just start using the other relations I have. What are the other relations? There's the uncapability relation, that if any one of these vertices gets connected back to itself, it's 0. And there's the multiplication relation, that if 2 of these are connected to each other by at least 8 strands, we can cancel them out and get some Temperley-Lieb stuff. And so now we just need to see that somewhere along the outside of this n-gon we've created, we have an edge with 8 or more strands. Well, and here, in fact, we have more than one. We have an edge with 9 strands and 13, and another one with 9. OK. So combinatorially, you can prove that if you take an n-gon and you triangulate it, then there's some triangle in there which has 2 sides that are along the edges of the original n-gon. OK, so there's a vertex there that doesn't connect to anything except its 2 nearest neighbors. OK, and then the pigeonhole principle says that one of the edges coming out of that has at least 8 strings. And so we find that location, and we apply the jellyfish relation. No, not the jellyfish relation, the multiplication relation. And now we have an n-gon with fewer generators, with a smaller number of vertices around the outside. And so we keep doing that, and we end up with some multiple of the empty diagram. OK, so this is an example of an evaluation algorithm. And in subfactor planar algebras, these are very interesting and important. If you're going to use generators and relations to present a subfactor planar algebra, you always have to make sure that what you get is the right size, right? And this evaluation algorithm procedure tells you that it's not too big. And then there's this sort of mechanical way of embedding it in a path algebra that tells you that it's non-trivial. And once you've done that, you've constructed a subfactor planar algebra, and now you can construct subfactors without even knowing what a subfactor is. OK, thank you. Yes?
Go back to the slide where you have the generators and the
Yeah.
So how come the first diagram that you have, it has, how come that is not trivial? The very first one, the S enclosed in the circle.
Ah, right. So this star has moved. OK, that's the only difference between these two is the position of the star. And it's a little hard to see from this diagram, right? But you could, the star is like the starting point, right? The star, way back in the definition of planar algebras, the star tells you how to line up things if you're composing them. What this is saying is that if you have some generator S in here and its star is in this region, if you need to change which region the star is in, you can kind of rotate it around. But every time you rotate 2 clicks, you pick up a factor of -1.
Okay, that's
Yeah.
Okay, so I think a few slides before this, to be a subfactor planar algebra, you said there had to be an adjoint with a trace.
Yes.
So in Temperley-Lieb, like I understand the trace is like kind of closing up the diagram. And then you just proved later that like Temperley-Lieb basically covers all of them. But are there
You're
different
right. I
types of
forgot to say what
traces?
that adjoint was. It's a reflection, a horizontal reflection, right? So you take whatever diagram you have and you just flip the top and the bottom. And you take the linear extension of that.
And so the trace here, is that always visualized as like closing the diagram, or are there different
Yes.
types?
So anytime you have a planar algebra, that diagram where you close the diagram up like that is going to be a trace.
And those are the only traces that you have?
I would not say that.
This planar algebra captures something. Should we say features of the so like planar, it's graph theorems.
Mm-hmm.
I think it's like planar algorithm is capturing how graphs are
Embedded. Yeah. So, so this must be true, right? This must be why Von Jones started drawing these pictures. So way back in the beginning, we talked about inclusion and conditional expectation. Here we go. And I think this was really kind of where Von started from, right? Envisioning inclusion as adding a string, envisioning this conditional expectation as connecting up the strings like this. And I think that this is kind of, if you're looking for like, how do planar algebras capture something intrinsic about subfactors, this is where you have to look. And that's kind of where you're starting from. Yeah.
Could I please see the slide again with the theorem that you proved with your collaborators? I want to try to understand what it was you were proving about that
Yeah.
relations.
So here we go. Right. So this is a generators and relations presentation of a particular subfactor planar algebra, and I haven't told you the properties we wanted it to have. What I'm just trying to call your attention to here is that simply that we can give this generator and relations and know that what we get back is a subfactor planar algebra.
If you don't mind, can I see the axioms of a subfactor planar algebra again?
Yeah, and I didn't actually list quite all of them. But there's the one-dimensionalness, and then there's the existence of the adjoint, and the fact that when you define the inner product of x and y as the trace of y star x, that this is positive definite.
Did your jellyfish algorithm prove this, essentially?
The jellyfish algorithm proved the one-dimensionalness. We took the existence of the adjoint and the positive definiteness of the inner product as part of our axioms. Like, this should really say that the positive definite planar algebra generated by these generators and relations. is subfactor planar algebra. Yes?
For Temperley-Lieb, there's a preferred radius pointed up. Is that always true that there's a preferred closing up?
What do you mean by that? You mean like the trace?
All the strands in this way, if you could connect them.
Yeah, yeah. I think if you're just dealing with Temperley-Lieb, you shouldn't even necessarily think of that as preferred, right? There are a bunch of other ways, right? You could first rotate it by 2 clicks and then do the same thing.
Preferred in the sense of, that's how you want the trace.
Yeah, yeah, yeah. But
There's always a good choice for that when you're doing a trace.
if you have a planar algebra, then you can always interpret that particular diagram as a trace. And that one, plays nicely with the multiplication we also chose. So.